In physics, an operator is a function over the space of physical states. As a result of its application on a physical state, another physical state is obtained, very often along with some extra relevant information. The simplest example of the utility of operators is the study of symmetry. Because of this, they are a very useful tool in classical mechanics. In quantum mechanics, on the other hand, they are an intrinsic part of the formulation of the theory. Operators in classical mechanics. In classical mechanics, the movement of a particle is completely determined by the Lagrangian or equivalently the Hamiltonian, a function of the generalized coordinates q, generalized velocities and its conjugate momenta. If either L or H are independent of a generalized coordinate q, meaning the L and H do not change when q is changed, which in turn means the dynamics of the particle are still the same even when q changes, the corresponding momenta conjugate to those coordinates will be conserved. Operators in classical mechanics are related to these symmetries. More technically, when H is invariant under the action of a certain group of transformations G, the elements of G are physical operators, which map physical states among themselves. Table of classical mechanics operators equals. Where is the rotation matrix about an axis defined by the unit vector and angle I? Concept of generator. If the transformation is infinitesimal, the operator action should be of the form. Where is the identity operator, is a parameter with a small value, and will depend on the transformation at hand, and is called a generator of the group. Again, as a simple example, we will derive the generator of the space translations on 1D functions. As it was stated, if is infinitesimal, then we may write. This formula may be rewritten as: where is the generator of the translation group, which in this case happens to be the derivative operator. Thus, it is said that the generator of translations is the derivative. The exponential map, the whole group may be recovered, under normal circumstances, from the generators, via the exponential map. In the case of the translations the idea works like this. The translation for a finite value of may be obtained by repeated application of the infinitesimal translation, with the standing for the application times. If is large, each of the factors may be considered to be infinitesimal. But this limit may be rewritten as an exponential. To be convinced of the validity of this formal expression, we may expand the exponential in a power series. The right-hand side may be rewritten as, which is just the Taylor expansion of, which was our original value for. The mathematical properties of physical operators are a topic of great importance in itself. For further information, see C algebra and Gelfand-Naimark theorem. Operators in quantum mechanics. The mathematical formulation of quantum mechanics is built upon the concept of an operator. The wave function represents the probability amplitude of finding the system in that state. The terms wave function and state in QM context are usually used interchangeably. Physical pure states in quantum mechanics are represented as unit norm vectors in a special complex vector space, a Hilbert space. Time evolution in this vector space is given by the application of the evolution operator. Any observable, that is, any quantity which can be measured in a physical experiment, should be associated with a self-adjoint linear operator. The operators must yield real eigenvalues, since they are values which may come up as the result of the experiment. Mathematically this means the operators must be Hermitian. The probability of each eigenvalue is related to the projection of the physical state on the subspace related to that eigenvalue. See below for mathematical details. In the wave mechanics formulation of QM, the wave function varies with space and time, or equivalently momentum and time, so observables are differential operators. In the matrix mechanics formulation, the norm of the physical state should stay fixed, so the evolution operator should be unitary, and the operators can be represented as matrices. Any other symmetry, mapping a physical state into another, should keep this restriction. Wave function equals. The wave function must be square integrable, meaning and normalizable, so that two cases of eigenstates are, for discrete eigenstates forming a discrete basis, so the state is a sum. where psi are complex numbers such that psi2 equals psi equals probability of measuring the state, and has the corresponding set of eigenvalues I is also discrete, either finite or countably infinite, for a continuum of eigenstates forming a continuous basis, so the state is an integral. Where c, I, is a complex function such that c, I, 2 equals c, I, c, I, equals probability of measuring the state, there is an uncountably infinite set of eigenvalues A. Equals linear operators in wave mechanics equals. Let I be the wave function for a quantum system, and be any linear operator for some observable A, then where A is the eigenvalue of the operator, corresponding to the measured value of the observable, that is observable A has a measured value A, I is the eigenfunction of if this relation holds. If I is an eigenfunction of a given operator A, then a definite quantity will be observed if a measurement of the observable A is made on the state I. Conversely, if I is not an eigenfunction of A, then it has no eigenvalue for A, and the observable does not have a single definite value in that case. Instead, measurements of the observable A will yield each eigenvalue with a certain probability. In Bra-Euroket notation the above can be written. In which case is an eigenvector, or eigenkit. Due to linearity, vectors can be defined in any number of dimensions, as each component of the vector acts on the function separately. One mathematical example is the del operator, which is itself a vector. An operator in n-dimensional space can be written where EJ are basis vectors corresponding to each component operator ALll. Each component will yield a corresponding eigenvalue. Acting this on the wave function I. In which, in Bra-Euroket notation, equals commutation of operators on I equals. If two observables A and B have linear operators and, the commutator is defined by. The commutator is itself an operator. Acting the commutator on I gives. If I is an eigenfunction with eigenvalues A and B for observables A and B respectively, and if the operators commute, then the observables A and B can be measured simultaneously with infinite precision, that is uncertainties, simultaneously. I is then said to be the simultaneous eigenfunction of A and B. To illustrate this, it shows that measurement of A and B does not cause any shift of state, that is initial and final states are same. Suppose we measure A to get value A. We then measure B to get the value B. We measure A again. We still get the same value A. Clearly the state of the system is not destroyed, and so we are able to measure A and B simultaneously with infinite precision. If the operators do not commute, they can't be prepared simultaneously to arbitrary precision, and there is an uncertainty relation between the observables. Even if I is an eigenfunction, the above relation holds notable pairs are position and momentum, and energy and time, uncertainty relations, and the angular momenta about any two orthogonal axes. Equals expectation values of operators on I equals, the expectation value is the average measurement of an observable, for particle in region R. The expectation value of the operator is calculated from. This can be generalized to any function f of an operator. An example of f is the twofold action of A on I, that is squaring an operator or doing it twice. Equals Hermitian operators equals. The definition of a Hermitian operator is. Following from this, in Bra-Euroket notation. Important properties of Hermitian operators include, real eigenvalues, eigenvectors with different eigenvalues are orthogonal, eigenvectors can be chosen to be a complete orthonormal basis. Equals operators in matrix mechanics equals, an operator can be written in matrix form to map one basis vector to another. Since the operators and basis vectors are linear, the matrix is a linear transformation between bases. Each basis element can be connected to another, by the expression, which is a matrix element. A further property of a Hermitian operator is that eigenfunctions corresponding to different eigenvalues are orthogonal. In matrix form, operators allow real eigenvalues to be found, corresponding to measurements. Orthogonality allows a suitable basis set of vectors to represent the state of the quantum system. The eigenvalues of the operator are also evaluated in the same way as for the square matrix, by solving the characteristic polynomial. Whereas the n identity matrix, as an operator it corresponds to the identity operator for a discrete basis, while for a continuous basis, equals inverse of an operator equals, a non-singular operator has an inverse defined by. If an operator has no inverse, it is a singular operator. In a finite-dimensional space, the determinant of a non-singular operator is non-zero, and hence it is zero for a singular operator. Equals table of QM operators equals, the operators used in quantum mechanics are collected in the table below. The boldface vectors with circumflexes are not unit vectors, they are three-vector operators. All three spatial components taken together. Equals examples of applying quantum operators equals, the procedure for extracting information from a wave function is as follows. Consider the momentum p of a particle as an example. The momentum operator in one dimension is. Letting this act on I we obtain. If I is an eigenfunction of, then the momentum eigenvalue p is the value of the particle's momentum, found by. For 3 dimensions the momentum operator uses the nabla operator to become. In Cartesian coordinates this can be written. That is, the process of finding eigenvalues is the same. Since this is a vector and operator equation, if I is an eigenfunction, then each component of the momentum operator will have an eigenvalue corresponding to that component of momentum. Acting on I obtains. See also. References.